Hi, hello. Let us discuss in this lesson about flywheels once again. In this design of flywheels, objectives of this lesson, on completion of this lesson, you would be able to know the design of flywheel and how to calculate angular velocity, radius of gyration, coefficient of fluctuation of speed, kinetic energy of flywheel, and some of the simple problems. First of all, let us see the design of flywheel. And the design of flywheel includes the design of size of flywheel, that is its diameter and mass of rim and its width and thickness, size of hub, external diameter and internal diameter, and the design of arms, number of arms, and major axis and minor axis of arms. We are going to design in this. Now it is the flywheel. If you see, the various parts of this flywheel are, this part is the shaft, and over this is the hub, and the internal diameter of the hub is nothing but the shaft diameter, or we can call it the hub bore diameter of the hub. And now these are the arms, different, say here, these are the arms, and this will be the rim. This will be the rim, and it is the mean radius of the rim it is. So this is a simple about the flywheel. And now size of flywheel here, and here in case of size of flywheel we are going to determine the rim diameter and also suitable rim cross section. That means width of the rim and thickness of the rim also we are going to get in this. That means cross section of rim may be obtained by considering the centrifugal stress in the rim of the flywheel. That means from this we are going to determine diameter of the flywheel and the rim cross section of the flywheel, right, by using centrifugal stress. So the centrifugal stress is equal to Fc, where Fc is the centrifugal stress, is equal to rho v square in Newton per meter square, where v is the peripheral speed of rim in meters per second. That is already we are aware that the formula for peripheral speed is equal to pi dn by 60. And rho is the density of rim material in kg per meter cube. And v is equal to, by already told in this peripheral speed of the rim is nothing but the pi dn by 60, where d is the diameter of the rim in meters and n is the speed of rim in revolutions per minute. From the above equation, diameter may be calculated. By using this, you can calculate the diameter of the rim. And now mass of rim. So mass of the rim, m is equal to pi d, which is the circumferential length of the rim, and a is the cross-sectional area of the rim, and rho is the density of the rim material. So here a is the cross-sectional area of the rim, that is nothing but the width of the rim into thickness of the rim, right? So b is equal to width of the rim and t is equal to thickness of the rim, and rho is equal to density of rim material in kg per meter cube. So with this formula we are going to calculate cross section of the rim, that means width of the rim and thickness of the rim, by using this mass formula. Now size of hub. Size of hub is equal to, that is internal diameter of the hub is nothing but the shaft diameter, that is d, small d, and external diameter of the hub is equal to d1 is equal to 2 times of shaft diameter or bore diameter of the hub. So L is equal to length of the hub, which is nothing but the 2d to 2.5 times of the shaft diameter. And similarly, where d is equal to diameter of the shaft or bore of hub. And next is, from this you can calculate the hub dimensions, that is shaft after internal as well as external diameters, and length of the hub also we can calculate with this. And now design of arms. Cross section of arms is usually elliptical with the elliptical cross section, which is having major axis A is equal to 2 times of the minor axis. A is equal to 2 times of B, where A is the major axis of the elliptical cross section and B is the minor axis of the elliptical cross section. And the number of arms required may be indicated as below. That is, n is equal to 4. Number of arms is equal to 4 up to 400 mm diameter. If it is the less than 250 mm, we are going to use solid disc flywheel. If the flywheel size is, that means diameter of the flywheel is less than 250 mm, then we are going to use solid disc flywheel. But whereas up to, that means 250 to, if it is up to 400, the number of arms are 4, whereas number of arms are 6 for a diameter from 400 mm to 3000 mm. And similarly, n is equal to, number of arms is equal to 8 for diameter above 3000 millimeters, that is 3 meters above. In such case only we are going to use 8 number of arms. So this we must remember. So cross section of arms, cross section of arms. So here you can see this is the figure, and this is the width of the rim and thickness of the rim, and here it is outer diameter of the rim, and this will be the shaft diameter. This will be the outer diameter of the hub, and this will be the length of the hub. And design of arms. In case of design of arms, the cross section of the arm is designed by considering bending stresses. Bending stresses, it means in order to find out the maximum bending moment, the arm is assumed as a cantilever beam fixed at hub. Once again, the arm is assumed as cantilever beam fixed at hub and carrying a point load at the free end of the rim. So the load on each arm is equal to, that is W, load on each arm, W is equal to T by R into N, where T is equal to torque and R is equal to rim arm length, let it be, and N is equal to, rim diameter radius, and N is equal to number of arms. So R is equal to mean radius of the rim, and T is equal to torque transmitted, N is equal to number of arms, and small r is equal to radius of hub. So maximum bending moment at the hub, capital M is equal to T by Rn into R minus R. T by Rn into R minus R. So here in this case, for this maximum bending moment, there should be some resisting moment, that is FB into Z. FB into Z. And these are to be equated with each other. That means this is a resisting moment and this is a maximum bending moment. And these two must be in equilibrium condition not to avoid the failure of arms. So for elliptical cross section, section modulus is equal to Z is equal to pi by 32 B into A square. As we are already aware that B is equal to A by 2, if you substitute B is equal to A by 2, then we will get pi into A cube by 64. So there is a section, this is a section modulus for elliptical cross section. So where A is equal to major axis, B is equal to minor axis. Assuming A is equal to 2B. and equate the maximum bending moment to the resisting moment, then with this equation, the value of major axis may be calculated. That means because torque is there for us, and R is also should be there us, and N is also there, and the radius of the outer radius of the hub is also known for us. Only unknown is A, which is the major axis of the arm. Then only we are going to calculate the major axis of arm. Minor axis is half of the major axis. Now let us see some of the problems relating to the flywheels. Here is the one problem. A flywheel has a mass moment of inertia 800 kg meters square and running at 350 revolutions per minute. The coefficient of fluctuation of speed is 4%. Determine the fluctuation of energy that the flywheel can control. So moment of inertia is given for us, I is equal to, and the speed is equal to N in terms of N, that is 350 revolutions per minute, and the coefficient of fluctuation of speed Ks is equal to 0.04, I think. So remaining, we should calculate the fluctuation of energy dE. So let us have the formula and have the solution for this. Moment of inertia 800 kg meter square, and speed N is equal to 350 revolutions per minute, and angular velocity omega is equal to 2 pi n by 60. With this you can calculate angular velocity in radians per second, and coefficient of fluctuation of speed Ks is equal to 4%, that is 0.04. And now kinetic energy, change in kinetic energy of flywheel is equal to fluctuation of energy, that is maximum fluctuation of energy dE is equal to I Ks omega square. Ks is there for us, I is also there for us, omega we calculated. After substitution of these three values in this formula, you will get fluctuation of energy in joules, that is 800 into 0.04 and 36.65 square, that you will get this much of 42,983.12 joules upon fluctuation of energy. Right, problem 2, let us see. A solid disc flywheel, a diameter 0.4 meter diameter and 100 mm thick, is made from cast iron of density 7 into 10 to the power of 3 kg meter cube, kg per meter cube. So determine in this case moment of inertia of the flywheel and kinetic energy at 1000 revolutions per minute. So here thickness is there for us, and diameter of the rim d is also there for us, rho is also there for us. So moment of inertia of the flywheel is equal to mass into square root of the radius of gyration, mk square. I is equal to mk square. If mass is there for us, then, and also if radius of gyration is there for us, then we can calculate mass moment of inertia. Number 1. Number 2 is, here it is the solid disc flywheel, and in order to calculate the radius of gyration, so for solid disc flywheel, K is equal to capital D, that is diameter of the rim flywheel, by 2 root. So with this, that means diameter is there for us, K will be available for us, and density is also there for us. So mass we have to calculate. Mass is equal to also we can calculate. Let us see. Diameter of the disc flywheel is equal to D is equal to 0.4 meters, and thickness T is equal to 100 mm, and the density of cast iron is equal to 7 into rho is equal to 7 into 10 to the power of 3 kg per meter cube, And now let us have mass of the flywheel is equal to rho AT. Rho AT. This formula we must remember. Rho is the density, A is the cross-sectional area of the flywheel, and T is the thickness of the rim. So rho is equal to pi d square T by 4, where A is equal to pi by 4 d square. This should be D value. This should be D. So rho is there for us, and pi is there for us. D is also there for us. T is also there. Then you can calculate your value for mass. So mass is equal to 87.96 kg. After getting, and radius of gyration k is equal to d by root 2, then you will get a radius of gyration as 0.1414 meters. So moment of inertia I is equal to mk square. So m is there for us, k is also there for us, then you will get 1.76 kg meters square. And next second is kinetic energy of flywheel. That is, n is also given for us in revolutions per minute. And k is equal to half I omega square. I is also there for us. Omega we can calculate by using n value to pi n by 60. Also we will get, so 1 by 2 into I is equal to 1.76 into 2 into pi into 1000 by 60 whole square. You will get kinetic energy 9650.3 joules. This is the kinetic energy of flywheel. So with this completed second problem also. And third problem, let us see the third problem. So the initial speed of flywheel on a punching machine is 120 revolutions per minute. Punching operation takes 2 seconds and requires 22 kilojoules of energy. So the speed must not fall below 90 revolutions per minute. That means the maximum speed is 90 revolutions per minute. The driving motor supplies 3000 watts at 115 revolutions per minute. The loss of energy due to friction is 20% of that supplied. Determine the moment of inertia of the flywheel, and then its radius of gyration if its mass is 650 kg. So here you can see punching operation time is there for us, and energy required also is there for us, and initial speed is also there for us, and maximum limit that must be used for operation is 90 revolutions per minute, and the motor supplied motor power is also there for us, as well as the speed is also there for us, and loss of energy due to friction is also there for us. With this you can calculate your radius of gyration, moment of inertia of the flywheel. So let us see, in punching of riveting machines, the work is done during a small part of the cycle. That means maybe 1 second or 2 seconds only. If it is driven directly by an electric motor or a belt, the motor or belt must be powerful enough to supply the energy consumed by the machine during the working portion of the cycle, and will run idle during the remaining part of the cycle. By introduction of flywheel between motor and driven machine, a much smaller motor or belt that must be used to supply energy at a practically constant rate throughout the cycle. That is the idea, right? And given that the initial, that means maximum speed of the flywheel is equal to 120 revolutions per minute, that is omega 1 is equal to 2 pi into 120 by 60 is equal to 4 pi radians per second. And maximum speed of the flywheel N2 is equal to flywheel N2 is equal to 90 revolutions per minute. So omega 1 is equal to loss of kinetic energy of flywheel is equal to, this should be N2 and this should be and this should be W2 omega 2, it must be, here it is 90 and it should be 3 pi radians per second. It should be minimum speed of the flywheel. So loss of energy of flywheel is equal to 1 by 2 I omega 1 square minus omega 2 square. Then you will get loss of kinetic energy as 34.541 joules per second, that is watts. Energy required for punching is equal to 22 kilojoules, that is 22,000 joules, and the time required is 2 seconds only. Power supplied by motor is 3000 watts and friction is 20% of energy supply. So power available for punching operation will be 20% loss. This is the supplied power and 20% loss is there. So 3000 into 0.8 you will get, that means 80% only we are using in this. The remaining is friction loss. That's why. So power available is 2400 joules per second. So energy available here is the 2400 into 2, that is 4800 joules. This is the available, but required is 22,000 joules. So energy supplied by flywheel, energy supplied by the required for punching is this much for 2 seconds, but supplied is this much, and for energy available is only 4800 only. That's why the remaining is 17,200 joules of energy supplied by only flywheel. That is already stored amounts. So loss of kinetic energy is equal to energy supplied for flywheel by flywheel or then you will get loss of energy 34.54 into I is equal to 17,200. That I is equal to 497.97 kg meter square. This is the moment of inertia of the flywheel. So radius of gyration K is equal to under root of I by M, that is you will get 0.875 meters. So that is the idea of getting this problem. So next is problem number 4. The speed of the crankshaft of an engine varies from minimum of 118 revolutions per minute to a maximum of 122 revolutions per minute. That means two speeds are there for us in N1 and N2, and we can calculate omega 1 and omega 2. A flywheel of mass 500 kg, mass is given for us. Radius of gyration 1.2 meters is key to the crankshaft. So with this you can calculate moment of inertia also. So if the work done per cycle is 60 kilojoules, calculate maximum fluctuation of energy in the flywheel. Then coefficient of fluctuation of speed, if the speed is, mean speed is 120 revolutions per minute, and coefficient of fluctuation of energy dE. So this you can calculate very easily without any difficult for us. Maximum speed of the flywheel N1 is equal to 122 revolutions per minute, omega 1 is equal to, after substitution of 122 RPM, you will get 12.78 radians per second. And similarly, minimum speed of flywheel N2 is equal to 118 revolutions per minute. And finally, you will get your omega 2 is equal to 12.36 radians per second. And mass of the flywheel M is equal to 500 kg. and the radius of gyration is equal to 12 meters, and moment of inertia I is equal to mass moment of inertia I is equal to mk square, and this should be square. So 500 into 1.2 square, that is 720 kg meter square ounce. This is the moment of inertia. So fluctuation of energy, that is change in kinetic energy, I half I omega 1 square minus omega 2 square, that you can substitute. Omega 1 is there for us, omega 2 is also there for us, I is also there for us. Then substitute the values, then you will get fluctuation of energy dE is equal to 3801.17 joules. And similarly, coefficient of fluctuation of speed Ks is equal to omega 1 minus omega 2 by omega. And mean speed in revolutions per minute also given, omega also to be calculated. Then you will get omega is equal to 2 pi into 120 by 60, that is 12.57 radians per second. After substitution of the omega 1, omega 2 and omega, then you will get coefficient of fluctuation of speed as 0.033. Right? This is the coefficient of fluctuation of speed. Next is coefficient of fluctuation of energy dE. Coefficient, sorry, Ke, that is equal to Iks omega square by E. Then you will get, and work done already given for us per cycle. So that's why I is also there for us, Ks is also there for us, omega is also there for us, and E is also there for us. Then coefficient of fluctuation of energy is equal to 0.235. So this is all about the problem. Next is fifth problem. The turning moment diagram for a petrol engine is drawn to the following scales. So turning moment 1 mm is equal to 5 Newton meters, and crank angle 1 mm is equal to 1 degree. By multiplying this, you will get the area of the turning moment diagram. That means 1 mm square into 1 mm into 1 mm is equal to 1 mm square. That you will get 5 Newton meter of torque transmitted, right? So now the turning moment diagram repeats itself at every half revolution of the engine. Half revolution means 180 degrees, and the areas above and below the mean turning moment line taken in order are 295, 1, 2, 685, 40, 340, 960, 270 mm square. So determine the mass of 300 mm diameter flywheel ring. So when the coefficient of fluctuation of speed is 0.3% and the engine runs at 1800 revolutions per minute, also determine the cross section of the rim when the width of the rim is twice the thickness, assuming the density of rim material as 7250 kg per meter cube. So here the various distribution of energy about the mean torque line for turning moment diagram is given for us. That is, one is the 265 and another is 685, and it is 40 square and 340 square, 960 square and 270 square. Here it is there. So it is, you can calculate energy at point, let energy at point A is equal to E, and energy at point B is equal to E plus 295, and energy at C is equal to E plus 295 minus 685, and at D is equal to, and so on. If you go on here at G point G, energy should be E only. So with this, you will get at on maximum point on this turning moment diagram. One is the minimum point. If you take the difference of these maximum and minimum energies at various points, then you will get fluctuation of energy or maximum fluctuation of energy. That is D. Right? Let us see the solution. So rim of the flywheel D is equal to 300 mm, and radius of gyration K is equal to D by 2, because the diameter is given for us. that is k is equal to 0.15 meters, and coefficient of fluctuation of speed is also given for us 0.3%, that is 0.003, and speed of the engine n is equal to 1800 rpm. So angular speed omega is equal to 2 pi n by 60, that you will get after substitution. 1800 in the formula, we will get 188.4 radians per second. The scale for turning moment is equal to 1 mm is equal to 5 Newton meters, and for crank angle 1 mm is equal to 1 degree, and convert this into, that is radians, pi by 180, you will get 1 mm square is equal to 5 into pi by 180, then you will get 0.087 Newton meters for 1 mm area of the turning moment diagram, right? So energy areas represented below the mean torque is considered as negative and above as positive. Below the mean torque line is negative, above the mean torque line is positive. So let E be the energy at the commencement of cycle, that is at point E. And at point B, energy at point B is equal to E plus 295, as I told you already. And energy at C is equal to E plus 295 minus 685, that is E is equal to E minus 390. And energy at D is equal to E minus 90 plus 40, that is E is equal to 350, E minus 350, sorry. At E is equal to, we will get same method, E minus 350 minus 340, that you will get E minus 690. And energy at F is equal to E minus 690 plus 960, that is E is equal to 270. And energy at G is equal to, finally we will get E also once again. E plus 270 minus 270, that you will get E only, right? So observing at various energies at various points, energy at A is equal to E, energy at B is equal to E plus 295, energy at C is equal to E minus 390, energy at D is equal to E minus 350, energy at E is equal to E minus 690, and energy at F is equal to E plus 270, and energy at G is equal to once again A. If you observe these distribution, energy at certain point will be more and energy at certain point will be minimum. That is energy at, if you observe this at point B, energy at point B is the highest value, that is E plus 295, whereas energy at point E is equal to E minus 690. This is the minimum energy, whereas this is the maximum energy. If you take the difference of this energy at B minus energy at C, then you will get your fluctuation of energy. Let us see. So maximum energy corresponding to point B, E plus 295, and the minimum energy corresponding to point E, that is E minus 690, then fluctuation of energy D is equal to E plus 295 minus E minus 690, then you will get 985 mm square. As we are already aware that 1 mm square is equal to 5 Newton meters. If you multiply this with the 5, then you will get energy in Newton meters. That is 985 into 0.87, as we had 1 mm square is equal to, that you will get 85.69 Newton meters. That is D is equal to IKS omega square. Omega is there for us because of the 1800 rpm is given for us. So Ks is also there for us. I is also there for us. Then I, you have to calculate, energy is there for us. Then you will get the moment of inertia is 0. After substitution of dE, Ks omega square, then you will get I value 0.8047 kg meter square. Let M be the mass of the flywheel. M is equal to I by K square. I by K square, whereas I is there for us in this and K is also there for us. Then after substitution of these values, M is equal to 35.76 kg. This is the answer for mass of the flywheel. So right. So mass of the flywheel, m is equal to volume into density. That is, volume is equal to T into B is the area, and pi d is the circumferential length of the flywheel, and rho is the density. Then you will get where T is equal to thickness of the rim, B is equal to width of the rim, that is equal to 2T as given. After substitution of all this, m is there for us, rho is also there for us, D is also there for us. Then after substitution, we will get thickness is equal to 51.2 mm, that is B is equal to 102.4 mm. After substituting all the values, then you will get your cross section also from this question, right? So next is problem 7. Design a CI flywheel for a single cylinder double acting steam engine that deliver 145 kilowatts at 120 revolutions per minute. The fluctuation of speed plus or minus 1.5% of the mean speed, and the maximum fluctuation of energy per revolution is 12% only. The mean diameter of the rim is 2 meters. The density of cast iron is 7.25 kg per centimeter cube. So solution here is mean speed is given for us 2 pi by n by 60, that is 12.56 radians per second. And similarly, energy delivered per revolution P into 60 by n, where P is the power transmitted. That is also given for us 145 into 60 by 120. Then you will get 72.5 kilojoule per revolution. Otherwise, 72,500 revolutions per joules per revolution. So fluctuation of energy dE is equal to Ke into E. That is, K is also known for us, E is also known for us. Then you will get fluctuation of energy as 8700 joule per revolution. And dE is equal to I Ks omega square. I is equal to dE by Ks omega square. Then you will get I is also 1838.3 kg meter square. Mass of rim m is equal to I by K square. This is also will get. Then mass of the rim is also 1838.3 kg. Dimensions of the rim. So let T be the thickness of the rim, width B the width of the rim, and mass of the rim m is equal to volume into density, that is pi dt P into rho, and B is also known for as 2T. Then you will get, so density of rim material rho is equal to 7.25 grams per cc, then 7,250 kg meter cube, and then T is equal to, after substitution of all the values, you will get 0.142 meters and 142 millimeters. Similarly, by using this formula, B is equal to 2T, then you will get B value as 284. With this, you got everything. And the shaft, hub, and key design. And shaft is, assume Fs is equal to 40 Newton, for that Fs is equal to centrifugal stress. So diameter of the shaft is equal to D is equal to 36.5 into under root cube root of P by NFS. By substitution all the values, you will get diameter of the shaft 113.67, that is D is equal to 114 mm. So this should be, you should have certain knowledge for assumption of this Fs. Shear stress. External diameter of the hub. So this is the shear stress in the shaft. Shear stress in the shaft. This is the shear stress in the shaft. You must remember this value. External diameter of the hub D1 is equal to 2D. So that is 2 into 114 is equal to 228 mm. And length is equal to 1.5, 2D to 2.5D. Then you will take 2.5D also, right? That's why 2.5 into 114, that is 285 mm. And the dimensions of the key, width of the key is equal to d by 4, 114 by 4. And thickness of the key d by 6, 114 by 6, then 19 mm. And length of the key is equal to 0.5 d, that is 171 mm. Assume n is equal to number of arms is equal to 6 for 2000 diameter, then BM, maximum bending moment at hub is equal to T into R minus R by R into N. This is already known formula for us, that is torque is equal to mean torque. So that is after substitution in formula, P is equal to 2 pi nt by 60, then you will get torque, mean torque is equal to 11,538.73 Newton meters. And Z is equal to section modulus for elliptical cross section, pi by 32 b into a square, whereas A is the major axis, B is the minor axis, which is equal to a by 2. After substitution of b value in this, pi a cube by 64, and the resisting moment is equal to bending stress into section modulus. Then equate this equal to maximum bending moment formula, equate to 1 and 2, then you will get FB is equal to pi d power to the cube by 64, T is equal to pi a cube, sorry. This A is equal to, after bringing this to this side, you will get your major axis 132 mm for the arm. And from this also you can calculate minor axis, this half of this one. That is, you can say simply 76 maybe. Right, with this concluded the lesson. 7 problems we have seen in this lesson, and also design of flywheel also we completed. Now let's have the summary of this lesson. In this lesson we learned design of flywheel and size of flywheel, mass of rim, size of hub, design of arms, and some of the problems we completed in this lesson. And let us have a small quiz on this lesson. Centrifugal stress induced in rim is given by Fc is equal to rho v square, P is equal to FcV square, omega is equal to GFcV square, G by omega is equal to FcV square, which is the right answer, say centrifugal stress. So as per our lesson, the A should be the right answer, Fc is equal to rho v square. Let us see the answer. So Fc is equal to rho v square is the right answer. This is the right answer, A. Next quiz. Generally the number of arms in a flywheel 3, 5, 6 and 7. Generally. So let us see the answer. So 6 is the right answer, C. The kinetic energy of a flywheel. Here is the one assignment. Some of the assignments, let us see. The kinetic energy of the flywheel rotating at 150 rpm. Speed is given for us, and the energy is also given for us. The radius of gyration is 0.5 meters. What should be its mass? So energy is there for us in this. So generally kinetic energy is equal to half I omega square. Omega you can calculate with this, and the joules is also there, I omega square. So with this I you can calculate by using kinetic energy Ke is equal to I half I omega square. So with this you can calculate I value from the kinetic energy formula, and then from I is equal to mk square. K is also there for us, only m is unknown. Then you can calculate mass of the flywheel. So that is the simple problem. And the rim of a flywheel of mass is there for us, and mean diameter 1.2 meters. Neglect the weight of the hub and arms, calculate the moment of inertia of the flywheel. So simply mean diameter is given for us. So if you take the removed flywheel, then it will be not, this is not the solid disk flywheel, that's why it is 1.2 meters diameter. K you can calculate by taking the half of the mean diameter. K is equal to 1 by 2, 1.2 by 2, that is 0.6 meters, and mass is there for us. Then moment of inertia is equal to I is equal to 4000 into 0.6 whole square. That you will get your answer. So next is a solid disk flywheel, 0.5 meters diameter and 12 centimeters thick, and can be made from cast iron. This type of problem already done in the solved problems. You can solve this problem very easily. A flywheel rotating at 600 rpm does 1950 joules of work for revolution. The coefficient of fluctuation of energy is equal to, given for us, Ke, and the coefficient of fluctuation of speed also given for us, Ks, and mass of the flywheel is 90 kg also given for us. Then power transmitted by the shaft on which the flywheel is mounted, you have to calculate. So maximum fluctuation of energy you have to calculate, and diameter of the flywheel also you can calculate. This also we can do very easily, and mass moment of inertia also we can calculate. We can solve this problem without any difficulty. So right, here are the answers are there. We can solve this problem. Thank you for patient hearing of this lesson. Thank you one and all. Please do the problems that given in the exercise assignment. Thank you, and one and all.